So next up is the very fun part that I know you all look forward to, and that is for us to talk about a titration. Okay, now a titration is something that is also known as volumetric analysis. Okay, and I'm just putting that terminology there in order to kind of indicate that we're going to be looking at things to do with volume and all that, right? So for a titration, the purpose of a titration is to find the concentration of an acid or base. Okay, so that's the sort of situation where a nutty professor or whoever it is walks into their laboratory and they see this jar that's just labeled hydrochloric acid, but it doesn't have a concentration, right? So they want to go find out, well, what is the concentration of this hydrochloric acid? Okay, so we first have to know what the procedure is going to be for our titration, right? So we usually start with a clamp stand, right, or retort clamp, and for that we tend to put a burette in that clamp stand. So the burette is going to have a little tap at the bottom, it's open at the top, that's where we pour the thing in, that's going to go in there, and then you'll see that there will be some markings along the side that will allow you to take readings. Okay, then below the burette is going to be an Erlenmeyer flask, right? In there we are going to put the indicator, right, the thing that's actually going to change color to tell us that we're done with the titration, and we're also going to put in there the analyte. Okay, now the analyte is that thing of which the concentration is unknown. Okay, so we don't know what the concentration is, we put it in there, and we're going to perform the titration in order to calculate its concentration. Right? So if the analyte goes in there, then what goes into the burette, so let me just write here burette. Okay, and here we have Erlenmeyer flask. I really don't know who Erlenmeyer was, or like why he's so important that his name is given to a flask. Because I mean, like, it's just a flask. But anyway, okay. So we've got the burette, and in the burette goes then the standard solution. Okay, right. So we've got a standard solution, right? And remember that a standard solution is a solution of which we know the concentration. So it's got to have a known concentration, and that's very, very important, because if we don't know the concentration of the standard solution, well, then we can't perform the titration. Okay, so what do we do here? Well, we drip the standard solution into this Erlenmeyer flask until we perceive the indicator changing color. Okay, that seems pretty simple. So what would we do? All right, so let's say, for example, the initial amount that we had for the standard solution was up there, right? Oh, right, and then afterwards we saw that at the end we had that, right? So the difference between those two things is going to be the volume of the standard solution that was used, okay? And then the volume of the analyte that was used, we are going to know that because, well, we measured it out in order to put it in the Erlenmeyer flask, right? So the standard solution, we knew the concentration, we knew the volume, and for the analyte, we knew the volume, okay? Now, if we know what the standard solution is and what the analyte is, we can write a reaction equation for it, right? And from the reaction equation, we can use a molar ratio. So if we've got the concentration and the volume, we can use that to find a number of moles. Now, if we know the number of moles of one thing, we can find the number of moles of the other thing using the molar ratio, right? So then we can calculate the number of moles of the analyte, and if we've got the volume and the number of moles, we can go find the concentration. And that's the idea behind the titration. Okay, now we've got some terminology. Now, the first bit of terminology is the end point. Okay, Now the end point is when we actually cease to do the titration. It's when we're done, right? And the link, the thing that tells us you're done, is when the indicator changes color. Okay, so the end point is going to be when the indicator changes color. Okay, now another important thing is the equivalence point. Okay, now the end point is something that happens on the macro scale that we can see with our eyes. The equivalence point is what's happening inside the solution that we can't see with our eyes. And the equivalence point is, you guessed it, when things are equivalent, right? So that's when all of the acid has neutralized all of the base, right? Excuse me, and then neither of those things are going to be in excess, right? So that's the equivalence point. Now, in order for us to be able to use a molar ratio, right, that means that all of one has to have reacted with all of the other. Okay, so it's very important that we end our titration at the equivalence point, right? So a successful titration is going to be one where the equivalence point coincides, happens at the same time as the end point, right? So the indicator has to change color when all of the acid and all the base has actually reacted, and that's something that we are going to look at in detail when we talk about the hydrolysis of salts. Okay, but first, let's do a calculation here. So we've got a titration, and 25 centimeters cubed of a standard solution of sodium hydroxide of concentration 0.3 mole per decimeter cubed neutralizes 16 centimeters cubed of sulfuric acid, and we've got to go find the concentration of the sulfuric acid. Now, firstly, we've got to write the reaction equation in order to be able to use a molar ratio, right? So sodium hydroxide reacts with sulfuric acid, okay, and that's got to give us Na2SO4 because sodium is single positive, right? And we're going to get some water, right? And in order to balance that, we're going to have to put a 2 there and a 2 there. Okay. Cool, right, so that's our balanced reaction, right? And then we can either do this a slightly longer way or a shorter way. I'm going to do both just for the concept, right? So we can start by looking at this and saying, okay, we've got a volume that we know and we've got a concentration that we know. Fantastic. Right, so for the sodium hydroxide, we can go calculate the number of moles. So the number of moles of sodium hydroxide is going to be equal to, so we know that C equals N over V, which means that N is going to be equal to CV, right? So we can take this 0.3, and then we've got to be careful. The volume has been given to us in centimeters cubed, and we have concentration in moles per decimeter cubed. So the centimeters cubed has to be converted to decimeters cubed, and we do that by dividing by 1000. So this is going to become 0.025, okay? And then the 0.3 times the 0.025 is going to give us an answer of 0.0075 moles. Okay, so that's the moles of sodium hydroxide that reacted, okay? So now, because we have a balanced reaction equation, we can go and use a molar ratio, okay? So we can say that sodium hydroxide is in a ratio with sulfuric acid of 2:1. For every two sodium hydroxides that react, one sulfuric acid is going to react, right? So if this is 0.0075, then we've got to go and divide that by 2 in order to get the number of moles of sulfuric acid. So that's going to be 0.00375. Okay? And now, because we know the volume of sulfuric acid that reacted, we can go find the concentration, which was the ultimate goal, right? So we can go say C equals N over V, right? That's going to be the 0.00375, right? And then again, the 16, we've got to go and divide by 1000, right? So if you do that, you get 0.016. Okay, and let's see what we get. 0.00375 over 0.016. And now we get 0.234375. Okay, so we can just round that and say that this is then 0.23 moles per decimeter cubed. Fantastic. Okay, so that is basically how the titration works and how the calculation works. Now, we can combine this into one formula, right? So we can say that the NA over NB is equal to CA over VA over CB VB. And those of you that are very mathematically astute, you can actually go and derive this from the process that we just went through, should you choose to do so. Now here, the NA over NB is always going to be in the molar ratio. So we don't actually need to go and calculate the number of moles. We can just go and use the ratio. So NA to NB is 1 over 2, right? So that's the implied 1 here and the 2 there. The CA is what we're trying to find. The VA was the 0.016. The CB we knew, that was the 0.3, and the VB we also knew. Okay, and that is then something that we can calculate. So we can go 0.5 times, that's 0.3 times that 0.025, and then go and divide that by the 0.016. And you will get exactly the same answer. So the CA is equal to 0.23 mole per decimeter cubed. Okay, so in a test or exam situation, you've got to do two things. You've got to get everything right, hopefully, and you've got to do it within the allotted time, right? So if it is possible for you to save a bit of time by doing something in a more efficient way, I highly recommend that you do that, right? So I did show this method just for the understanding, right? But this method here is a little bit quicker, as you saw. So I encourage you to use that method when you've got these titration questions.